Riemann sums and finding the area under a curve using geometry was an excellent introduction into Calculus 2. But to really get into the meat of Calculus 2, we need to start talking about antiderivatives. An antiderivative is exactly what it sounds like. It's the opposite of the derivative. It's like undoing the derivative. Just like multiplication and division undo each other, addition and subtraction undo each other, natural log and e undo each other, antiderivatives and derivatives undo each other. So let's start with 4.8. The function capital F is an antiderivative. So we use this capital to help us realize what we're doing. So the capital F is the antiderivative. So the derivative of f prime, capital F prime, is the function. So you're thinking about going back and forth between the derivative and the function. The antiderivative undoes the derivative and gets back to the original function. And we always need to add a constant, plus c. What I mean by that is take a look at these two functions. When I take the derivative of f of x equals x squared plus 5, I get the derivative is 2x. When I take the derivative of f of x equals x squared minus 4, I also get a derivative of 2x. So notice what happens when I take the derivative, my constant function goes away. Therefore, I'm losing my constant. So when I take the antiderivative, I always have to say plus some constant. Okay, so now we're going to talk about taking the antiderivative. The antiderivative undoes the derivative. So what I'm trying to figure out is what gives me a derivative of 0? Well, any constant gives me a derivative of 0. In this one, I'm looking for what gives me a derivative of negative sign. So think about the function that you're going to differentiate to give negative sign. Hopefully you came up with cosine of theta. Now, as we said before, you always need to account for a constant. So it's plus c. Because the derivative of cosine theta plus 4 is still negative sine theta, the derivative of cosine theta plus 100 is negative sine theta. So it's really important to add that plus c when we do the antiderivative. This next one's pretty tricky, so we're going to come back to that one in 1 second. Let's do ones that are a little bit more accessible for a moment. Let's try the one that we did on the other page, 2x. So what gives us the derivative of 2x? Think about what do I differentiate to get 2x? Hopefully you came up with x squared. And again, we always want to say plus c to account for that constant of integration that we lose. All right, let's try another one. What about let's say x cubed. What would give me the derivative of x cubed? Well, you know it has to be to the 4th. But I don't have a 4 here. When I take the derivative of this, I get 4x cubed. But I don't have a 4 here, so I need to be able to cancel out the 4 somehow. And the way I'm going to cancel out the 4 is by dividing by 4, or multiplying by 1/4. And then again, we'll do plus c. So let's take a look at taking the derivative of this, and hopefully that will make a little bit more sense. So when I take the derivative of 1/4 x to the 4th plus c, the 4 comes down, 4 times the 4th, and then I get x cubed, and the c goes away, which is just x cubed. We're still holding on to this one. We'll talk about that in 1 second. So this is like the anti-power rule. That's not really what it's called, but that's what we're going to call it, is the anti-power rule. And the anti-power rule says, just like the power rule, before I do that, I'm going to talk about the power rule. The power rule tells me that if I want to take the derivative of something that's x to the n, the way I take the derivative is the n comes down and I subtract 1 from the exponent. So to undo the power rule, I need to use this anti-power rule. So instead of subtracting 1 from my exponent, I add 1 to my exponent. And instead of multiplying by n, I divide by n plus 1. The only exception to this rule is the natural log. If I have x to the negative 1, or 1 over x, the antiderivative of 1 over x is the natural log of x plus c. That's the only exception to this rule. So let's take a look at the one from the other page. I think it was C. And maybe H. Is the square root of x, or x to the 1/2. So the first thing we're going to do is add 1 to 1/2. So 1 plus 1/2 is 1.5, or 3 over 2. And then I multiply by the reciprocal or divide by 3 over 2. You can think about it either way. And I can't forget my plus c. So now let's take the derivative of this and see what we get. The 2/3 times 3 over 2, and then 3 over 2 minus 1 is 1/2, and the c goes away. So 2/3 times 3 over 2, those cancel each other out, and I'm just left with x to the 1/2. This anti-power rule looks really complicated, but once you get the hang of doing it a couple times, it's actually quite easy. So here's a common table of anti-power rules, or antiderivatives. I wouldn't say that you need to memorize these. I think I always just figure them out instead of actually memorizing them. What I would say that you want to memorize is maybe looking at the arcsecant and the arctan. Those are ones that we don't necessarily use often, but when you do use them, they're really easy and useful to have. So those are probably the ones that I would say memorize. Everything else I think you can figure out if you understand derivatives. Okay, now we're going to solve for c. So if they give me the differential equation, the derivative equals x squared plus 2x plus 1 with the boundary conditions that x equals 1 and y equals negative 1. Verify the solution. So what we're going to do is first find the equation. So if I know this is the derivative, I need to take the antiderivative, which would be x cubed and then times 1/3, and then x squared and 2 over 2, and then 1x and plus c. So I'm just going to reduce this so it looks a little bit prettier. So 1/3 x cubed plus x squared plus x plus c. And now this is my original equation y. They're giving me the conditions that y equals 1, x equals 1 and y equals negative 1. And what we're going to do is use those conditions to solve for c. Kind of like how you used to solve for y equals mx plus b. You plug your point in and you solve for b. We're doing the same thing now, except for with c. So negative 1 equals 1/3 of 1 cubed plus 1 squared plus 1 plus c. All right. Negative 1 equals 1/3 plus 2 plus c. So 2 1/3, or what's that? 7/3 equals negative 1 plus c. All right, let's subtract the 7/3 from both sides. And I'm going to write this as 3 over 3. So that's negative 10 over 3 equals c. So my constant is actually negative 10 over 3 given these initial conditions. So now my original equation is going to be y equals 1/3 x cubed plus x squared plus x minus 10/3. And it wants me to verify that I'm correct. So let's take the derivative of that. The 3 comes down, 3 times a third, x squared plus 2x plus 1, the negative 10/3 goes away, and the 3 over 3 I can cancel, so I just get x squared plus 2x plus 1. So yep, it looks like my problem was done correctly. So this is my check. You're going to want to do the check each time for a long time until you feel really good about taking the derivative, the antiderivative, I mean. You really want to spend the time taking the derivative, even if you don't do it on paper. If you just do it in your head, you'll see that it allows you to become more natural when going between the derivative and the antiderivative. The last part of section 4.8 is about rectilinear motion. I know that sounds really scary and weird, but we're just going to think about what we already know. We know we have a position function, and the derivative of position is velocity, and the second derivative of position, which is the derivative of velocity, is acceleration. When we anti-differentiate, we do it in the opposite direction. The antiderivative of acceleration is velocity. The antiderivative of velocity is position. So that's what this is telling us, and that's also what this is telling us. Let's try example 5. Find the distance s of an object at the origin. So we're at the origin. If its acceleration a is this, and we know that the velocity of v of 0 is 4, and the position of 0 is 1. Okay, so the first thing we're going to do is take the antiderivative of the acceleration. So my acceleration is 8t minus 3. The antiderivative of that is my velocity. So it's going to be t squared, and that's going to be 8 over 2 minus 3t plus c. So 4t squared minus 3t plus c. And now we're going to figure out what the c is in this exact case. So this is my velocity. By using, right here they told me v of 0 is 4. So that means when t is 0, my v is 4. So my c is 4. So now I have my velocity function is 4t squared minus 3t plus 4. Now to find the position function, I'm going to take the antiderivative of that. I'm going to use x of t as position. Sometimes they use s, sometimes they use x. It really depends on what book or what test we're looking at. So I feel like the AP test uses x more often than anything else to show that it's the position function. So that's what we're going to use as well. So I take the antiderivative of this, 4/3 t cubed minus 3/2 t squared plus 4t plus c. Even though these are the same letter, it's supposed to be a 3. Even though these are the same letter here and here, they're dealing with two different constants. So it's probably better to write it actually as c1 and then c2. So now I'm going to use the second condition that they gave me right here, where they told me that when t was 0, my position is 1. Now that I just saw that, it looks like they actually want me to use s for position here. Again, no big deal, we can change position. Okay, so when this is 1, we get 4/3 times 0 cubed minus 3 over 2 times 0 squared plus 4 times 0 plus c2. So my second constant is 1. So then my final position function is 4/3 t cubed minus 3/2 t squared plus 4t plus 1. So we're just, instead of taking the derivative twice to find the acceleration, we're taking the antiderivative twice to find the position. But same basic idea.